Perfect. Wonderful. Thanks, Erin, and welcome to the third panel discussion in this series on scalable computing for pandemic preparedness and resilience. And on behalf of the entire NSF Prepare panel and team, I welcome you to this discussion. Today, we're going to talk about data consideration. As everyone knows, data is one of the key challenges where we would discuss about processing it, accessing it efficiently. And today's focus is going to be about how do we do and tackle data effectively on HPC, that is high performance computing systems. And we have a very distinguished set of panel members for this morning. First is Kirk Jordan, who is an IBM distinguished engineer and an IBM executive at IBM Research in the data-centric solutions in the TJ Watson Center. He's also the Chief Science Officer for IBM Research in the UK. In addition to Kirk, we also have Phil Blood, who's a Senior Director of Research, and Phil directs the PSC research and supports teams spanning biomedical applications, AI, and big data, among others. Finally, we have Aditya Prakash, who's an associate professor in the College of Computing at GATech. So, we have a distinguished set of panelists, and we'll have a more detailed introduction as they give us their thoughts on this. I'm hoping we have this where we have the three panelists will present today. If you have any questions, we'll perhaps have a one or two after the panel members present. And we have a significant amount of time for us to have a very interactive discussion. So I would invite all the audience to save some of the questions for the discussion as well. So without further ado, I invite Kirk Jordan to provide his insights on some of the data challenges and how on his experiences there. So Kirk is, as I mentioned earlier, at IBM Research. He's a distinguished engineer there. And some of his key interests are working in advanced computing architectures, and he oversees a lot of development of applications here. He has investigated and develops new concepts in the areas of high performance computing and provides leadership in high-end computing, data-centric cognitive computing and simulations in a wide variety of areas spanning computational fluid dynamics, systems biology, and high-end visualization. So thanks, Kirk, and please take it away.
So hopefully you're seeing one screen and not the speaker's note screen. So
we see the screen right. Perfect.
Awesome. That's number one. Number two is I have two disclaimers. The first disclaimer is that I have a cough. It has nothing to do with COVID or anything like that. But if I cough and you got your headphones on and you get that in your ear, I apologize ahead of time. Second off, the other disclaimer I have is I've been in HPC for like eons and dating way back to the previous century. And one of the things that I learned way back when was data is very important, but it's also my enemy, okay? Filling up disk farms and crashing machines was never a good thing to do. So trying to avoid the data was one of my missions. So now you're asking me to talk about data considerations. And I do think, I do want to state right up front that data is, I think, is becoming more and more important. One of the problems that we face, though, as I'll go through to the charts now, and that is really the data in the high performance computing arena. Those of us that did high performance computing, we really focused in on the speed of compute. And that was yesterday. And today, to get anything done is you got to do the data and the compute together. And that's why I have, oh my God, right? And so I don't have answers. I have suggestions of how we need to maybe approach this. There's all sorts of things going on. We need to take advantage of a variety of things. So one of the big things, and I'm borrowing a lot heavily from my team in the UK in putting together these slides, because there's all sorts of things happening. It's really exciting. And data is becoming really the most important piece of this, yet high performance computing can help with that. However, we can't make everyone a high performance computing expert. So how do we avoid that? And people are, and particularly Lakshmi knows this and others in the biological sciences, the tendency is to start working on your laptop and you develop your tools and things there. But then suddenly when you try to use a lot of data, things don't flow because you can't fit them on your laptop anymore. So it's not just, the compute intensive simulation that we're looking at, but we're really looking at what is the entire workflow. And we in HPC tend to look at the compute intensive piece and try to speed that up. But that doesn't work anymore. So more data intensive and oriented towards data is what we look at. HPC architectures have accelerators in them, GPUs. GPUs are great. They do matrix multiplies. Well, what is neural networks and machine learning and AI? But lots of matrix multiplies. So they're very good at that, but they don't have a lot of storage for the data. So we bump into the convergence of the hardware, software, and the workflows. And I mentioned cloud really is going to, I think, accelerate the adoption, not by HPC users, but by other users. And they will try to make their cloud, their cloud version of their application or workflow much more accessible to others, but they may not take advantage of the HPC learning that we have. So I have a couple pictures here suggesting some things. We have on-demand provisioning of HPC resources by simulation services on top of Red Hat, OpenShift, or Kubernetes Cloud, and the subsequent deployment of the workflow here in the upper right-hand corner. Also, we need to take advantage of the architecture. Okay, so in the lower right-hand corner, can we do more and more within the machines themselves, within the memory of the machines? We have all sorts of architectural features. The disks, we have multi-core CPUs. Can some of the cores be working on transferring data so that the workflow flows nicely, moving it to non-volatile memory within the system itself, to CPU memory, to accelerator memory, which could be a GPU, or it could be an FPGA, or it could be a neuromorphic chip, who knows? And so the bottom line comes down to data handling needs more consideration at all levels. The life science health folks build from tools for ease of use, and HPC folks build tools for performance. And the two of these organizations needs to come together. And so I could stop here. And one of the things in coming together that we probably need NSF and NIH and a few others to kind of support is kind of this model that the National Cancer Institute set up years ago, setting up centers that were physical science oncology centers, okay, where they brought the oncologists together with the physical scientists. The way you propose those centers, you had to have the physical scientists be the lead PIs. And we may need something like this where we need not the HPC guys to be the lead PIs, but we need the end users. And when I say the end users, I don't mean the data scientists and those folks. I'm kind of talking about what was mentioned yesterday in the afternoon session, that the folks like the policymakers need to get, we need to hear what they need, what they think they need. All right. And I think that's really important. So let me move on to the next slide. All right. And so feeding the beast, some thoughts on this. So this comes from experience, not just from myself, but from others. As I said, you know, I was notorious for filling disk farms. Just filling disk farms really gets people angry at you. So I tried to avoid the data as much as I could by doing all sorts of tricks, and I'll mention a few of those here. But the actual data storage requirements on an HP system may be significantly higher compared to the initial input data that you try to move over. So one of the issues that we have is moving the data around. I mentioned cloud in the last chart. And that kind of scares me, because where's the data? If it's not where you've got your compute power, you may have issues moving it all over the place, okay? But here's an example where you start with a 0.85 terabyte compressed data set that then gets uncompressed and becomes 3.2 terabytes of data set. And then you generate additional 9.2 terabytes of intermediate data, and you see a 15x increase. And this is a simple example. Low adoption HPC capable tools, or you could say it the other way around, the tools that the people who need to ask questions about policy don't fit with the HPC tools, okay? So standard compression algorithms like gzip is inherently sequential, okay? So we can't use the parallel decompression that you would normally do with an HPC system. HPC IO is not optimized for life science data and healthcare data, okay? So in the following sense, you know, the simulation data is a binary format. You know, we like to think in HPC, you know, we've got our floating point, whether it's double precision or single precision, and that's great. But the life sciences, it's sequence data, it's electronic health records, it's, you know, stuff that's, you know, well, while the HPC file systems can be POSIX compliant, they don't perform well on the metadata. And issues for bioinformatic workflows, they may generate thousands of lines or thousands of files even, non-POSIX alternatives like object storage, in-memory storage. Active research is an area for active research here, and active research is going on, but there's no one solution yet to perform on some level HPC class file systems. I just, you know, we see these pictures all the time about water treatment for COVID-19 tracking. I stole one from Massachusetts here where I live. And, you know, here's the data flowing around. And we'd probably like to have more data so we could answer more general questions for the policymakers and get ahead of the game so that they can respond. And the net of this is, how can HPC really, because it's going to be time to the answer is the real key issue here. Someone asks a question, how fast can you get them the answer? And you don't want to take shortcuts necessarily. So I'll mention one other thing here. Oh, I went too far, too fast. So we did some work with the team in the UK did some work here. And I just want to point out that, you know, you start out with your human in a box here, and they're coughing, like I cough from time to time here, and they're spreading, you know, the viral infection all over the place. So how can you understand that data? And so this what you see here is there's a little movie here I can play. This is in the cabin of an aircraft, and it's streaming information out. And of course we have GPUs on HPC machines. So what we wanted to do is, well, we can do the visualization. We don't have to move the data all over the place. What if we can do the visualization? So we have our workstation that shows us the end product, but the simulation, the analytics, and the visualization are all happening within the node that it's been worked on. And so that cuts down, because now we're only have to moving pixels around. So that helps, as opposed to we got the workstation, we do the simulation, we send it to a disk, we bring up another workstation, we do the analytics, and then we do the visualization post-processing. That slows everything down. All right, let me quickly finish up here. As when we introduce AI and HPC in the pipeline, we need the throughput and the validation. So we start looking at compound libraries and applying novel AI methods to that. We do the molecular docking, and then we move it down to the molecular dynamics. So this is going to require some HPC computation. And then we get into high-end kind of calculations. This is work that we're doing in collaboration with Oxford. And then we want to do experimental validation. So now we got to bring the validation data involved. And so you see the throughput here kind of winds down. So I think data and data considerations are important. I think we need to really think about who needs to participate in the effort so that it works for everyone. You go into a hospital and, your doctor is struggling with, just using, his PC to understand what's going on. And, I'm lucky in the sense that my doctors here in the Boston area are pretty savvy guys. But elsewhere, they may not quite be so savvy. So there's a lot of work here. I think we kind of ignore the data. And particularly in the HPC world, we tend to be focused on how can we make things go faster. But if we're going to get the whole workflow to go faster, we need to be thinking about how do we speed up all the components and use the data the way that people who are the end users need to see the data. So with that, I'm going to stop.
Thanks, Kirk. I think this was very insightful about having the whole end-to-end pipeline of science workflow, and needs to be optimized, including the entire data pipeline that's part of it. Any questions for Kirk that you may have?
I thought that I saw something in the chat. Is that right or not?
Yeah. Again, I posted that folks could add to the chat as well. If not, we'll move on to the next panelist, and we'll come back. We'll have time for questions for all our panelists. Next up is Phil Blood, who is the Senior Director of Research, and Phil directs the Pittsburgh Supercomputer Research and research support teams, including biomedical applications, AI, and big data user support for scientific applications. Phil also leads the Anton project at PSC and co-directs the National Center for Genome Analysis Support and serves as the co-PI for Exceed. Take it away, Phil. Thank you.
Thank you, Venkat, and thank you, Kirk, for the great introduction. Thanks for inviting me to participate in this really interesting panel discussion and effort. And I appreciate, Kirk, you set me up for some of my comments talking about the need to work across the different agencies to address the challenges. We're talking about pandemics here, and so this is an NSF workshop, but clearly NIH will have a lot of important things to bring to the table in terms of working together to solve these kinds of challenges. And so I wanted to focus on that, and this is born directly out of my direct experiences working at PSC, where we've primarily been traditionally funded through National Science Foundation, working as part of Exceed, building the various supercomputing systems that have been funded by NSF over the years and supporting the national research community in doing that. But we've had a small but now also actually starting to grow quite a bit effort in supporting NIH efforts and providing resources to the NIH community. In particular, for me, it's come through a recent engagement in the NIH Common Fund, which is funding high-risk, high-reward type endeavors that I'll share some experiences. So I'll be sharing some experiences from all these different areas and some thoughts that I think for me hit a couple of themes. One, I really will be focusing on making HPC more accessible to different types of users. And so how do we make the relevant data that people would need to address the needs of these pandemic situations and other research needs, make these data more findable, accessible, interoperable, reusable, these fair principles on the HPC resources. And then, as I just said, given the obvious role in NIH-funded efforts in the pandemic response, how do we help align the interests of NSF and NIH to support generation, dissemination, and use of data on HPC resources? So starting off, near and dear to my heart is Exceed. I've worked for, I guess, over a decade now in, if you include TeraGrid and then Exceed, I guess just Exceed is over a decade now, isn't it? So with John Towns and other wonderful colleagues there. And I think Exceed has done a lot to make important data and tools available to the research community in a way that does open it up to more than just the HPC experts and the computational experts. I've had a particular role in this, working through Exceed's extended collaborative support service, which I think was a fantastic model for bringing, Kirk, you also mentioned you don't necessarily want the HPC experts leading the way, and you need the scientists and sometimes the policymakers and others who know what they need, helping, being a key contributors, at least equal contributors to that process. So that was the spirit of this extended collaborative support service in Exceed, where computational science experts that were funded across all the Exceed sites were matched up with research teams, and there was a real collaborative engagement there, where the strengths and expertise of the computational experts, the researchers, came together to build tools, to optimize code, to get access to code and tools through what in Exceed and in follow-on projects in the NSF world we refer to as science gateways. Others talk about data portals and other things along these lines to give access to the tools in the back-end HPC resources to those who don't really care what they're running on, what they're using. They just want to get their science done. So I'm going to share. I'm sharing some of these experiences, and with each one I have a recommendation. And so one of my recommendations here is we talk about being prepared for people to be able to effectively use data to support efforts to address pandemic research and emerging needs associated with these emerging issues in society, that I feel like it would be important to continue to fund a group of computational science experts who can help research groups make their data fair and available for use on HPC resources, similar to the efforts that have been successfully employed in the Science Gateways programs that have been funded, and also some other projects that I'm going to talk about on the NIH side. So another project that I lead is to make available a special purpose supercomputer for biomolecular simulation. Some of you may have heard of the Anton system that is developed by D.E. Shaw Research, and which they have made available over the last, again, decade or so, have made available at PSC for the national research community. The importance of this resource is that it's about 100 times faster than a traditional supercomputer for biomolecular simulation. And so when the COVID-19 HPC consortium formed, we wanted to make it available through that mechanism, in addition to the normal mechanism, through which it's been made available through review panels convened by the National Academy of Sciences. Anton's a wonderful resource, but it's very limited. And so one thing that we've tried to do to improve the impact of Anton, which has been used to, for some of the COVID-19 research and other important biomolecular simulation studies, is to make the data more fair and available to the community. So this is a part of our ongoing effort in our current funding with Anton, is to take all the molecular dynamics trajectories that have been generated over the last 10 years and make those accessible to the research community. We can do that retroactively and brings a lot of value there, but also now going forward, we want to intentionally collect metadata and make the data available in the formats and such in a way that it's maximally findable and accessible to anyone who would want to reanalyze these data. These are great for AI machine learning algorithms that have, have very long trajectories, long time scales, so that you can start to use those to then predict time scales further than we can simulate in terms of the biomolecular behavior. And so, so this experience leads me to a recommendation to consider providing incentives and resources for research groups as they're getting funded, and we all are required to do data sharing plans and so forth, but specifically to make their data fair and accessible through the various HPC resources. And so here's I think a really important point to come together, with NSF and NIH talking to each other about leveraging this great investment that NSF has made in all the supercomputing HPC resources, and how do we better leverage that across the board for all the research that's happening across the various agencies. Certainly we've done that in Exceed, and in the NSF systems have been supported. We've allowed anyone to come in, no matter what their funding source, and use those resources. But can we also help people to make their research results available on those resources in a more systematic way, so that people can then go use them and take advantage of the HPC resources to analyze and use those data and maximize the benefit and impact of those data. So, so that takes me to my next NIH project that I've been leading over the past few years, leading the infrastructure for an NIH Common Fund program called the Human Biomolecular Atlas Program, which has the modest goal of developing a open and global platform to map healthy cells in the human body, and that means basically 3D cellular resolution maps of all the tissues in the body. And so we're not going to get to that, in that complete human body in the time scale of this program, but we're trying to lay a foundation to do that. And so as part of that, PSE, together with collaborators at the University of Pittsburgh, have pioneered a flexible hybrid cloud microservices architecture to make the data that we're bringing in across many different single cell assays, both imaging and sequencing data, bringing in those data, making sure that they're fair, and also making them available across both on-premises resources at PSE, leveraging the supercomputing and the NSF investment there, and also the cloud resources, and making the tools go to the data wherever it makes sense. That Kirk also addressed that problem, just trying to optimize. We're always going to have to, if we're going to aggregate data across projects and such, some data is always going to have to move. But the idea is that to move the least amount of data possible. So if more data is in the cloud, then bring your data there. If the data is more localized on-prem, then we bring cloud data on-prem and can operate across those. So as part of this, we're also trying to develop some tools for using, so people can find the data. We want to make it easy for people to use the data and analyze these data, leveraging the on-prem resources at PSE or cloud, if that makes more sense, or I should say, or public cloud, because it's all cloud, it's hybrid cloud. So we're trying to develop frameworks there where we develop general framework that then people can plug in the last bit, depending on where they would deploy it, they would plug in, okay, we're going to use AWS S3 and plug that into as a storage resource. We're going to use, we're going to schedule things with Slurm and run analyses on-prem. So that's a compute resource we can plug in. And so I think another recommendation we do is think about how we encourage more development of modular and reusable frameworks for data management analysis that could span various types of resources or be deployed on various types of resources or even hybrid resources, bringing together public cloud and on-prem. All right, and then I think this is my last example. So this is really connected to this HubMap NIH project that I mentioned, where I mentioned it's a common fund project, and NIH is funding a lot of these. And there's a concern that, again, data gets siloed into a single project and it's only useful in the context of that project. And so NIH is funding this common fund data ecosystem effort to try to bring together the data across all the common fund projects and make those findable and accessible across all these data centers that they're funding, which HubMap is one of these. And so what we're doing there is submitting metadata according to a common standard that's been established there, so that in a common portal, researchers can go to one place to search across all the available data. And then we're also working on developing, using some standards that are being developed in the community for finding data. So there's I'm not gonna be able to remember the acronym properly, or the meaning of the acronym, but I believe it's Directory Resource Service, or DRS, that is a standard for pulling data between different sites, pulling or pushing data, so that, again, if researchers find data across these different projects, they can then bring it to a single computational platform, probably wherever their primary data is located amongst these different centers, bring the rest of the data to that site and analyze the data all together there. So that's another effort to make those data more accessible and useful on whatever computing platforms that researchers best fit the researchers' needs, and be able to leverage and find those data outside of the context of a single project. So the recommendation there would be to look at mechanisms, develop these fund mechanisms to facilitate the finding and aggregating of related data to open platforms for analysis. So that gets me to just overview of my initial thoughts and recommendations as I thought through some of the projects I've been involved in to continue to fund a group of computational science experts to engage research groups, help them make their data fair and available on HPC platforms, provide incentives and resources for research groups to make their data fair and accessible through HPC directly to those groups and the funding mechanisms, and then encouraging development of modular infrastructure frameworks for management analysis across public cloud and on-prem resources, fund mechanisms for facilitating finding and aggregating related data to open platforms for analysis. And then last one that is new here is explore and develop opportunities to leverage and combine NSF and NIH resources to make data fair across public cloud and HPC. So with that, I'll end and take any questions now or later.
Thanks, Phil. This is really insightful, and I found this extremely interesting. If there are any questions for Phil, we can take maybe a question or two now. The one question I had, Phil, is about you talked about incentives to provide researchers so that they can make their data available and with the right metadata, so that you can curate them and provide them to this is kind of a key requirement to help with any fairness properties going down the line. Can you share some thoughts about incentives that one can give researchers who run on systems?
So I guess my really, I don't know, hopefully it's not what's the right word? So so my initial thought, Venkat, with this was, I mean, I think it's more of a stick though than it's an incentive, but it'd be on the stick side. So I'd be happy to hear hear thoughts on the better ways of incentivizing on the nice side. But one is just to formalize some requirements, maybe more specific requirements as part of the data sharing requirements that come with the various solicitations that are put out between NIH and NSF and other agencies. So I think we're moving towards that. NIH actually has already updated their data sharing requirements, and my colleague at PSC has been on those panels. I don't think they're in effect yet, but I think maybe just giving more direct guidance on best practices there and what needs to be collected as part of the funding. And I guess the incentive there is that if it's a requirement for you to get for your funding, that you provide a plan for how you're going to do this, that you also make available budget as part of those, as part of the budget of that program, that people will allocate time and effort to actually do that. So that's my initial thought. I very much open to other thoughts, but I do feel like it would be really helpful if there was a way to align NIH and NSF in particular along those lines in terms of what they're requiring researchers to do. Many researchers are funded by both agencies, and if there was an alignment there as much as possible, and also specifically looking at how the platforms on which these data are made available. I will just say last comment and answer your question is that as part of this bringing our NSF perspective and their supercomputing resources that have been funded through NSF to this NIH program in HubMap, the solicitation that went out for this recent in December or in October of last year for the next phase of the infrastructure for HubMap specifically asked researchers to consider using these NSF allocated funded resources through Exceed and think about how they would leverage those in what they propose to do. So I thought this was really fun to see that come through and that engagement there.
Fantastic. And I think that this would be a good topic for us to dwell more in the panel discussion that we'll have later. But this is really insightful, and thanks, Phil. Our next speaker is Aditya Prakash. Aditya is an associate professor in the College of Computing at GATech, and his research spans data science, machine learning, and AI, with a real emphasis on big data problems in large real-world networks and time series data, and with applications to computational epidemiology, public health, urban computing, security, and web tools. And tools developed by his group have been used in several places, including Oak Ridge National Laboratory, as well as Walmart. So please take it away, Aditya.
Great. Thanks, Venkat, for the kind introduction. So are you able to see my slides? Just want to make sure.
Yes, we can see it. Go ahead.
Okay, perfect. Thanks again, and thanks for having me. I think my talk would be giving probably a perspective from a machine learning and a data science person, and how we think about some of the data sharing and data issues we have encountered in our work for the past couple of years as part of our COVID response, and what kind of tools we had to develop to address them. And I hope that can give I think complementary perspective to a more bird's eye view and policy recommendations we have heard so far. So the context of this talk is that one of our labs focus is to explore the performance and utility of data-driven methods in public health, spanning across, let's say, surveillance, interventions, vaccination, and so on. And the thesis, so to say, is that data from multiple sources is which we have seen in other parts of ML is often more sensitive to what's happening on the ground, can be complementary, and give a helpful perspective to other more traditional models which have been used. And also, more importantly, also I feel that as this is a really active areas, new data science and AI techniques can handle end-to-end learning, and are responsive to dynamic changes. I think that's one of the main reasons why we have been really interested in exploring the utility of such methods and what it can do in a real public health planning and response. So one of the, I'll talk about today mostly about only one example, which we have been involved in as a group on AI models for forecasting. I'm sure all of us have seen these COVID-19 trajectories and lots of, which have given us I think right now maybe they have gone a bit in the background, given that incidence rates are a bit low. But I'm sure we have all seen these dashboards by various groups, which have been really influential in helping us make sense of where the pandemic is at any given moment. So, at a very high level, real-time forecasting, I think if you ask a machine learner, you can think of it as just a time series forecasting problem. Obviously, that's grossly undersimplifying it. But at a very high level, you're given some incidents, right? Let's say death counts, mortality, and you want to predict, you're given till the orange line, and you want to predict what's going to happen in the future. Needless to say, this is pretty challenging, right? Like, for example, here, the curve looks like it might go down, but in fact, it started going up, right? So it depends on lots of different variables and factors which are pretty hard to predict. So it's a really challenging problem. And why forecasting? I think to this crowd, probably I don't need to have the slide, but just to remind ourselves, right? Like, this forecasting is interesting because it helps us provide an outlook to the future, which allows communities to allocate resources and budgets, like ICU beds, ventilators, inform public policy, improve preparedness, because it helps lay people to make decisions like, should I go to the grocery store, right? Depending on what kind of incidents I'm seeing in my locality, and so on, right? And that's public communication. So we as a group have been involved in, as several others have been involved in many CDC forecasting efforts down the years. We were involved in the ILI influenza-like illness predictions, and now after COVID started, I guess we have pivoted to, for the past couple of years, to COVID mortality and hospitalizations, and we have been submitting regular forecasts for the past 2 years. So, but why deep learning in this setting, right? As I said, it's flexible, scalable, efficient technology, which is we have found to be an excellent choice to model nonlinearities, which we encounter very so often in this space. And very, very crucially, I think we are able to incorporate different knowledge representations in a very modular fashion using deep learning. And I think this is a primary strength which we have, which has allowed us to incorporate these different data sources without really too much tweaking and too much changing the core predictive model. And it helps that it's an active research area. So the big picture problem which we are trying to solve, I would term it as, how do you give accurate, well-calibrated, and explainable predictions in real time? In pandemic forecasts. So that's really the core problem we have been interested in. So our team, GT Deep COVID at the CDC Forecast Hub, I saw that Nick was also a panelist yesterday at the workshop, so I'm sure he must have talked about it as well. So we have been performing pretty well in that Forecast Hub for the past couple of years, over 50 states. And but I think also very interestingly, from computing and data science viewpoint, I think it has also enabled a lot of methodological advances, which we are pretty excited about, including transfer learning. How do you incorporate expert guidance, uncertainty quantification, handling data quality issues, and how do you also handle it multi-scale dynamics? So I'll talk today about mainly the data quality issues and how that has motivated some of the solutions we have been looking for, and why exactly statistical and AI-based ideas can be particularly helpful in that problem. So we have had other impact, like won a few awards, and it's been also used in different settings now, and extended it to be used in campuses like at GATech and hospitals and so on. So the formulation, right? So the formulation of our problem is pretty straightforward. You're given partially observed, let's say, a mortality or hospitalization numbers till some day T, but we also have a lot of exogenous data sources, which are may be or may not be correlated with the incidence curves, right? And we need to predict, let's say, for in this instance, mortality for the next 4 weeks or 5 weeks, and these are typically called short-term forecasts. And that's what we have been up to, and for the next 4 weeks in future. And that's really the problem we are tackling. So it's important to remember we don't have historical data, right? So it's very hard. This makes it very hard to keep ready-made models and just deploy them in some sense, right? And that's why the models have to be nimble and able to adapt to these exogenous sources. So using different, I mean, a lot of thanks to all the volunteers all across the globe and in the US, we have been collecting a lot of different kinds of data signals. Many of them are public, some of them are not. So we have a very detailed data set, which we have on GitHub which incorporates around 35 signals across 50 states. Very importantly, we also incorporate the revisions for these signals. So we actually can see how the data has evolved week to week for the past couple of years, right? So this includes line list, the regular sources, to also like vaccine data, social surveys, and so on. So we built this operational framework called Deep COVID, which kind of has like 3 different modules. And I think this is again motivated by a lot of what we saw was important as we were talking to the domain experts and stakeholders as we were doing this. I mean, so there we have a data module which kind of deals with the data issues and ingests different data sources. Then we have this prediction module, which has a bunch of different models. And then we have this explainability module, which helps us understand why we made these forecasts and why we didn't make some other forecasts, right? And what kind of features and signals were important in helping us do that forecast for that week. So we can do both retrospective as well as analysis of real-time predictions as they are being generated by our model, right? So some of the lessons learned, right? Uncertainty is very important. Explainability is very important. And some of them might be very obvious, I think, when we hear about them. But I think, like, for example, we thought that the data would be chaotic, but we didn't really realize how chaotic that would be. And human input and feedback is also important. And I think it's important for all our pipelines to be nimble enough to make sure that these kinds of goals can be attained, right? And it can allow people to give their feedback, at the same time help them understand why the predictions are being made, and also give robust predictions in presence of noisy data. So I'll give you an example of the data problems just by using one particular source of data. Let's say the vaccine related data, right? So we have been using data from CDC and also JHU on the number of doses administered, and also this online surveys on Facebook, which I'm sure you must be aware of, which captures the attitudes as well as different kinds of adherence to or like vaccine intake, right? Have they taken intake? Have their friends taken vaccinations, and so on and so forth. So these online surveys have also captured some sort of behavioral variables like willingness to vaccinate their kids, or if the people are facing any systematic barriers to access based on where they are. Or maybe let's say language or schedule time constraints and so on. So a lot of rich different kinds of variables which has been captured by these kinds of surveys. But unfortunately, one of the biggest problems we faced in vaccine data was that it's limited, it's sparse, and it's siloed, right? And I think in some sense, this makes the job of learning very, very challenging, right? And as I said, they are also frequently revised and very, very noisy, right? And we have routinely seen very big updates and revisions to these kinds of data sets as we are going in real time. So hence, this leads to a lot of quality issues, right? So, and also there's low coverage for some regions, and they don't really, in some sense, capture the behavioral heterogeneity which we need to give more granular and point forecasts. So we have been also thinking about, like, for example, I mean, one thing to think about this is that is there a quality score which tells us is this data good enough to be used, right? And these kinds of ideas are big. It seems like in these kinds of extremely chaotic situations are very important. So how would we address these challenges, right? So I think I want to emphasize improved data collection, and I think there's a big role computing and HPC and in general data science can play in improving data collections and not just storage, because I feel and usage, because I think a lot of these things are from first. The problem starts from first principles, right? And if we address the data collection itself and make it easier for the data producers to do their job, I think that will reap a lot of rewards down the pipeline. Secondly, I think privacy preserving shareable analysis is very, very important, especially when you're working with EHRs and with hospitals. which we found again was very, very challenging, especially when we want to have really complex models. So it works well when you have simple models, but when as the complexity of the models goes, I think this is a very hard topic to handle. Right, I think more data at lower granularities and also data from other diseases is another technique we have used to make sure that we can use this multi-scale aspect of the thing to of the system to really address the data challenges. And also, I would also say from the AI and ML perspective, we need a lot of methodological advances to bridge ML with other more behavioral causal models and address these data challenges. So it's not just, so I think it gives you a very multidimensional, it's a multidimensional challenge, and I think it needs like efforts from multiple different directions to really tackle the underlying problem. One another thing which I want to emphasize is that I think which we found was that the temporal aspect of all of this, right? So for example, in data, the relevance of the data itself changes over time, right? For example, think of the importance of the signals of vaccine hesitancy or initial vaccination or third, fourth dose intake is different at different stages of the pandemic, right? And the survey data itself might still be updated. Maybe more questions are being added, more questions are being removed as we get different kinds of, as we are at different stages of the pandemic, right? So that means all these computing and AI models need to quickly adapt to the changing scenario, right? And that's a very important issue which we face. So that means updating models frequently is very important. And that's why scaling up is important, right? Because we need to be able to rescale and restart, in some sense, the models very quickly and quickly update them based on these new changes. So I think, so I'll talk a little bit about the scaling part, but also, I mean, there are other kinds of AI techniques like transfer learning, which can help you to transfer existing models to new emerging responses, which might be interesting here. So, okay, so as I promised, I mean, I'll quickly talk just about this particular very specific research problem of these, how do you handle the revision dynamics, right? So this is also called backfill in this space, which is like how do you leverage how the data itself is being corrected or revised to improve real-time predictions in the future. So in the forecasting, the typical forecasting setup, as I've talked about, you have this time series data, you have these exogenous signals, you have a nice, interesting model in the middle, and then you're trying to give these forecasts in the future, right? So this is really the standard situation. And for COVID, this might be, so this issue is not just for COVID, right? So this kind of revision dynamics are very common, especially for social science signals, like let's say employment, GDP numbers, which I think we typically think about. And these exogenous signals can be any of these. And the problem here is that the time series data is really the past data, right? So this is data which you have from the past, whereas the exogenous signals also are coming till the current week only, right? And you want to update this model with data up to the current week to make these forecasts. So the big issue here is that the past data which you have is itself getting revised, right? So they are not stable values. And so, for example, this picture shows how the number of doctors' visits due to COVID-like illnesses are changing for different states at each time point, right? So the initial data release gets revised over time. And the causes for these can be multifaceted, right? Human error, data instability, just because maybe there were some pipeline issues, delays, disasters. For example, when there was the Texas snowstorm last year, for a couple of weeks, I think the data was very chaotic, and then the data kept getting revised for another month after that, because people realized what errors were propagating. So it occurs, as I said, not just in epidemiology, but also in other social science situations. And the natural question we asked ourselves is that, can we kind of adopt and leverage these kinds of revisions to make our predictions better? So note that this kind of a problem is, I feel, very uniquely suited to statistical and AI kind of approaches, because the causes, as I said, can be multifaceted. So modeling them from first principles will not be trivial, right? Because the particular error in any particular data revision will be very hard to ascertain, right? But our hope is that maybe there are enough statistical regularities and patterns which we can adopt and leverage, which can help you improve your predictions, and that's what this work is about. So the unfortunate or the interesting thing, I guess, is that we found that not just the targets, which are just, let's say, COVID mortality, but also the features of our in our data set are also getting heavily revised. So for example, we looked at, let's say, this is mortality for the state of Texas. which for the week number 28 in, let's say, 2021. So that means 225 deaths was what Texas reported for as the mortality for week 28. And you can see for the next 30 weeks almost, the numbers steadily kept getting upwardly revised, and it kind of stabilized to eventually like around 400 for at week 52. So that means there was this is called the backfill phenomenon. And basically the backfill error in this situation is almost 45%. And the stability time is around 24 weeks. So that's saying that you need to really wait for a long time. And if you're really waiting for the data to stabilize, that's not really a viable approach, right? Because by that time, this predictions might itself not be useful at all. So that means you need to work under this kind of chaotic situation, but still give robust and meaningful estimates for the future. So we studied a lot of, so one thing here is that these kinds of patterns are only visible when you study, right, really large data sets, right? And we studied like around 40,000 real backfill sequences in the COVID's data set. And that itself raises other scaling issues, right? Because these are really, it's a really large data set and you need to do statistically significant analysis on that. But here are the main kind of, I would synthesize like the 4 main observations we found. The backfill error is significant, which kind of that's what motivated this work. But there's also a large similarity in backfill sequences, right, across regions and across different kinds of features. And I think this is an important observation. And also model performance is affected by backfill error. Again, this might be intuitive, but the interesting thing is it's affected by backfill error as well as model bias, right? And that's I think that's an important observation. But at the same time, model evaluation is also affected by backfill error. That means it's very hard for someone like CDC to say that this model is the best at this stage, because it might be using wrong targets to really evaluate that model. So this raises a lot of interesting questions of how do you improve both performance and evaluation. So that means modelers should leverage revision dynamics and can do that to improve performance. But at the same time, evaluators may also need to leverage revision dynamics to improve real-time evaluation itself. So we call this refinement as well as rectification. So we want to refine forecasts and rectify evaluation forecasts. So I won't go into detail about the model itself. I think if I give you the big picture, it's pretty, I think, clear what the model does. But at a very high level, it is trying to leverage the similarity which is inherently there in these kinds of backfill sequences, and then use those latent representations of these similarities to improve the predictions of the model. And the one thing I would like to highlight here is that you can plug in any model you want to improve its predictions. It can be a mechanistic model. We treat the model as a black box. All we need is the history of the model in terms of what it has been predicting for the past few weeks. So one thing here is, again, and this is where I think scaling issues come into picture, is that to enable this, we really have to think hard about how do you scale it up, right? And we have to use many tricks, primarily pre-training and fine-tuning, which I think improved our performance by up to 2x. And this would not be possible if we had not have access to HPC resources, right? And I think this tells the twofold problem, right? Like the models are going more complex, but at the same time, they're also are becoming more modular, and you need to quickly update them based on what you're getting at every week. So it's like the model has to do all 3 things. And I think tricks like pre-training and fine-tuning, I think, is a very promising direction there. So we call our method back to future. The good thing is, so we found that we could improve the performance of all the top models in that COVID hub. In fact, the best performing model, which is Ensemble, which is an ensemble of all models, we could improve its performance by almost over 15% in many states. So which is pretty significant. In fact, any of the top 5, if we had used our model on them, they could have been the best performing model in all the states. So that clearly shows that there is a huge signal which is there in the revision itself, and which should be systematically, I think, leveraged. So what's next, right? So I hope I've given you a sense of what kind of data issues we have encountered, and how I think methodological as well as I think computing techniques can be very helpful to resolve those kinds of challenges. So right now we have been focusing on exploring many other kinds of technical questions, including handling different sources of uncertainty, incorporating behavior from first principles, bridging with the synthetic data and simulated data, right? And also handling these dynamically changing data streams. One very important thing which we are trying to do in collaboration with some hospitals is to also leverage point of care private information, which again raises these interesting questions of how can we make these models which we have developed, can we leverage like techniques like federated learning and more private, differentially private techniques, which can scale up at different sites, right? And these kinds of issues is something we have been exploring recently. So, I mean, that website tells a little bit also about what we have been up to for the COVID response. I think this crowd would be very interesting. And also this symposium we had held last year, I think the report is on the website. So I'm sure that you might find many different points of, I think, contact, which you might be interested in how SAIS can really connect to different domains involved in this problem, but also at different scales. And I think that's an interesting point, which is like it's cross-cutting not just domains and disciplines, but also different scales of this problem. So thanks again for the invite. Thank you all to our students, collaborators, and also like computing repositories. Like we made heavy use of the PACE HPC at GATech. So that was crucial to enable this work for the past couple of years. Thanks again.
Thanks, Aditya. So we have, I think we should just go right into the panel discussion. Lakshmi, you have a question, and feel free to, ask the panelists.
Okay, thank you, Venkat. Great talks, all panelists. Thank you very much. I have a question that you may be kind of facing it regularly and probably have some answer. And, we have, we always want more and more and more and more, right? So there is data, there is more and more of data that we are getting. So is it more is more, or will it plateau at some point? I mean, do we have a sense that after some point, the information that I'm getting from the data is not significantly increasing? I mean, what is your experience with when you deal with all the data that you are getting in? Is that at some point you think information-wise it is saturating or more or less saturating? It's my question to all the panelists. Venkat, you can decide. Yeah,
I'll jump in first off. Yes, there's more and more and more, and there's going to be more and more and more, partly because we, as you know, Lakshmi, IBM being a technology company, we're going to enable with the internet, higher bandwidth, everything else, we're going to enable more to happen. Now, the question is more useful? That's really the question, right? And what can you get the pieces out that are useful without going through, and I think this is where the HPC community and the data science community and the end policymakers and end users that are going to make use of this need to all get together and go in, well, what's useful to those that need to make decisions? And maybe we can suck away, and I was having a discussion with a couple of colleagues that together we're working on a book. And one of the issues that we talked about data is right now, a lot of data is owned by companies and not shared. And so how do you incentivize them to provide, or are there mechanisms to, and this was brought up, I think, by Phil, can you look at taking useful information out without trying to get all the data? And we probably need all sorts of federated data schemes and whatnot. So that's my take on it, is yes, there will always be more, but it's a question how useful it's going to be. We're just flooded with data. I mean, all you got to do is look at my inbox and I just can't keep up with it.
Maybe I can,
yeah, go ahead.
I wanted to quickly add, I think it's a great question. And I think But I would say that this is not a static question, right? So maybe your model is saturating right now, and that data signal is not helping right now, but it can quickly change. For example, we found that in 2020, mobility was very, very crucial in the initial stages, but then its importance kind of decreased in helping us predict these mortality and incidence values. So I would say that yes, and that's a very important question in the sense that we need to build models which are robust and can also know what to not take into account, right? And tell the stakeholders when they should not trust the outputs as well. And that's one of the things we have been doing when we are trying to do this uncertainty quantification from different sources. Then we need to tell the model, and the model should learn when it should forget a source. But these are classic, I think, AI and data science problems, which I think a lot of methodological advances can be done. But at the same time, the models get updated, right? And that's why I think of these problems as not as static and really evolving. And I think it would be a mistake to just discard a data source just because it's not helping right now. And that's precisely why we need more. More is good. I mean, I never say no to data. So.
Those are great answers. I just wanted to add just an example from one of my contexts is this hub map, trying to make a cellular resolution map reference atlas of what is normal human tissue. And I don't know that in my lifetime we'll ever get enough data to do that. But it is important to have methods to analyze, how much is a particular new data set coming in, adding to our understanding. And I think this has a really practical application for us, because one of our mandates is we're never going to get enough. We have centers, they're funding a lot of centers to generate these data. We're also going to have to bring in as much as we can from other funded sources across internationally, consortia, individual research groups, and try to understand how is that data, what data will we bring in, how much is that data helping us to build this reference atlas and be able to incorporate it in there in a way where we understand, what value is this bringing, and so that also, I think, tracking that in our case, if we can demonstrate that and show that, it can also incentivize the community. We can, show them, if we can get, these kind of data, then this is going to fill a crucial gap in our understanding here. So if we can identify the gaps and where we're really missing coverage, and share that with the community, that can drive, interest in the research community to provide those things that we need.
Thank you. I see Madhav has his hand raised. Please go ahead. Thanks,
Venkat. Very nice talks. Thank you very much. So I had one question for all of you, and then one maybe for Aditya, but others probably would have a perspective as well. So maybe some background first. When we were using the supercomputers at Pittsburgh, and we really want to acknowledge the support we have received, Phil, from you and Sean and others. I said that yesterday, and I'll say it again, that without you folks, John's help and others, we would not have been able to do the kind of work we did in the last 2 years. But one thing we find is that the access to these machines appears to be non-trivial. So especially with Kirk around, they have announced a strategy of hybrid cloud. Our view is that we need to be able to harness multiple supercomputing systems in a rather nimble way. The reservation-based systems that we talked about yesterday sort of don't work in a perfect manner. We certainly need to get it harnessed. And the reason I bring it up in this session is that moving data across these machines as you try and carry out a workflow that Kirk and you mentioned appears to be somewhat non-trivial. I want to see what sort of solutions you folks are working on. So that's question one. My second question is an extension of Lakshmi's question, and probably all of you can answer. Having more data is an interesting question, right? And maybe to extend what Aditya says, and I'd like to hear his thoughts. Again, an example I would take is from stock markets, where the speed at which the data comes in and the kind of data comes in changes the kind of models that you can even build in the first place. And this is an ever-evolving situation, is the word Aditya uses. do you see what the logical fixed point of this dynamical system would be? Because the models keep getting better and better. They demand more data that requires you to collect more. So I was trying to see what you would conjecture as a normal fixed point of a system like this. In stock markets, people are starting to place their offices near to the exchange. That nanosecond seems to matter for their trade. So thanks. I'll listen to your answers.
Any takers for the first one? Who wants to go first?
So
go ahead.
Well, yeah, I think we're so I think mostly I can acknowledge, Madhav, the complexity and the challenges that you're talking about. I think we're pretty far from making seamless or non-trivial usage across multiple supercomputing sites for any sort of complex or large scale data. Really accessible and non-trivial. And so I think some of the things that we've talked about today could possibly help with that in terms of leveraging strengths of the on-prem supercomputing resources together with the strengths of a public cloud, and doing that in an intelligent way. I think could potentially help. You have on the NSF-funded open scientific access supercomputing systems. You have a lot of you have to balance this shared resource that's being made available at no cost directly to the researchers, access to that. So these reservation-based systems that you had in the cloud, you don't have that. You can pretty much scale infinitely, but that obviously comes with another cost and with some complexity. So can we play on the strengths? And I don't have the answer for this either, but can we look at ways that we play on those strengths to address some of the needs that you've highlighted there? That would be one thing to think about. And I had another thought, but it's gone now. Maybe it'll come back to me. So that's on your first question. Oh, I guess my other question was if you talked with Sean about this yesterday when he was presenting. I know that he is looking at for this next round of I know that people are looking at for the next round of the NSF funded things through access. How do we improve on the current systems and things. So he may have some thoughts on that if he didn't already share them with you.
Thanks, Phil.
Yeah, so I'll comment along the lines of, I think one of the things that we're trying to do as part of building out future systems, because they're going to be a combination of things, and we're going to add in more complexity with bringing in quantum computers at some point. Putting all that together is going to require some intelligence as to both where is the data, where is your compute, what kind of compute are you going to want to do, and all that. Do we have a handle on this? No. And actually that brings me back to a point for that Phil sort of satisfies in having some of these large centers. You create these critical mass of experts that can help us navigate through some of those issues. And I think that one of the ways to get a handle on this is start to investigating how can academia, industry, and government really work together. We always talk about that, but we never really do it. Okay, we're always kind of adversaries when we start working together. Everyone doesn't trust the other guy. So, I think that's where you want to build out these large scale teams that incorporate industry and academia and government to really, do the groundbreaking work that needs to be done, which, some of which we start out down one path, we fail at. That's okay, but we start learning what else will work and how to do that. In my several decades at this, I haven't really seen this work out all that well yet. But that's has to do with other things. It doesn't have to really do with the scientists, you know. So we need to bring the critical mass of different stakeholders together and just say, go at it and see what happens. So I hope that answers part of one of your questions. I'm not sure I answered the other one. I want to bring up a question that's related though, and that is when we start looking at on the international front, now data can't necessarily move from one entity to another. And so how do you get around that issue? That's another issue that we bump into.
Thanks.
And I'll touch the second question. I think it's a great question. I think of it like sometimes it's like Kolmogorov complexity, right? We don't know if we're there yet, and that keeps us in business. So that's a good thing. We'll always be needed. But I think at a big picture level, I would say this space is still in its nascent stages, right? So I think there's a lot of obvious, I think, next steps in the sense of what need to be done to go from a reactive stage to a more proactive stage. I think that would be something which I would say is a big step, that we are not always in a reaction mode, right? And I think that would be really great. And also at the same time, I think maybe the better question would be, instead of a fixed point, might be, are we above a certain level which enables these decisions which people need to take, right? Like, for example, I don't know whether we really need to predict to an accuracy of 1 or 2, right, RMSE, of how exactly the mortality and incidence to enable CDC or the stakeholders to make a decision, or for me to make a decision about what I want to do that day. So I think, so yeah, I mean, so that's, I guess, encapsulates my view. I think instead of trying to say that do we have the best model all the time, I think it's more about, can we go from reaction to proactive situations, leveraging, I think, what's the current sources and the decisions which people need to make. And I think that would be a constantly changing equation, because it also depends on a lot of societal constraints and political constraints. So I think that's why maybe it's unknowable, and that's okay, because as I said, that keeps us in business. So.
Thanks.
And indeed, and I would say that it's to Madhav, your first question, it's both a technology question as well as policy questions, right? You're trying to bring in diverse organizations, teams together and incentivize them. To a question about just allocations, right? You have different allocation mechanisms, different authentication mechanisms. That's something, again, that needs to be tackled. And I do know that there are several efforts towards kind of integrated infrastructure. I know in the Department of Energy, we are looking at how do the supercomputing centers and the experimental sites kind of work together. And I'm sure there needs to be more efforts going broader than that in the future as well. But several of these questions have come up in our plans towards it. So, and things that happened during COVID and trying to get access for, I would say, near real time or real time is all very key of them. So that's these are great questions. And I think Kirk kind of alluded to tackling international collaborations and sharing of data. There's a question from Arvind. Arvind, I could ask, or if you want, feel free to unmute and ask the question as well.
That is the design space of all possible.
Sorry, I think there was some this one going on.
Go ahead.
Yeah, I think one of the things that I'm mostly interested in is trying to understand from the panel as to, there is a lot of talk about federated learning frameworks that are out there. NVIDIA released one a couple of weeks back, and a bunch of people are doing a lot of work in that. But none of them actually really focus on privacy preserving approaches, or none of them really focus on the scale of the models. For example, some of these models can have billions of parameters, and what do you share, what do you hide, what do you not show? And I think there's a lot of questions surrounding those types of, frameworks that are out there. So wanted to hear the panel as to what their ideas were, or understand where do you think these frameworks are actually falling short when it comes to like handling some of these parameter hungry or parameter rich models, however we think of them.
So again, I'll jump in here. I think one of the issues is trying to get everybody trying to get their hands on the different models that could address these and just seeing how they work. But I like it was mentioned in my background bio there, I'm the chief science officer for IBM Research in the UK. So we have to deal with this all the time, going between two different countries. We have some people working closely with people at Yorktown, and then we have people in the UK, and they're all within the same company, but they have different backgrounds, and the question then becomes, about export control and all these other things that impacts both moving code and data, and then you try to go to different organizations within, like within the UK. Getting data out of the National Health Services is a lot easier than getting data out of similar places here in the United States. So, and that enables us to do some things we can do there that we can't do over here in the United States. So it's not just technology. I think this was just brought up. It's also policy issues that come into play, and how do you handle that, and can you keep some things private as well as allowing to access the data? Do we have to get into holomorphic encryption or something else to just be able to do things and but never actually see the data? So I don't have a good answer. All I know is it does give me a headache.
So I think, Arvind, I think that's a very important question. And I would probably think of it like, in my experience, as two questions hiding there, right? One is, I think, depending on the context, I mean, if you're talking about large databases, which are distributed across different sites, let's say hospitals. So I think, I feel there's a lot of current work, and there's a lot of stable patterns which you can leverage. And I think people, I mean, it's still not there yet. Probably a lot of things need to be done, but I think people are making a lot of strides because we are getting a buy-in from the hospital data holders itself, right? And but on the other hand, I would say federated learning is very important also when the data producers are not just hospitals, but people itself, right? Let's think of like apps, right? And where people are telling their own and like in some sense crowdsourced decisions and crowdsourced experiences, and I think which have to be leveraged, I think, for like a really dynamic system. And I think I think there's a lot of tension in terms of the value of a person's data, and also the value of the prediction or the model's output to that person, right? And I think there I have not seen really too many good success stories of balancing this trade-off to make it valuable enough for the person to actually interact and give that data to for the decision makers. And yeah, so I think that's how I would put it, that maybe there needs to be a convergence there from a usability point of view, but also from this technological point of view of making it cheap enough and agile enough to be deployed on a smartphone, but also usable enough for the person to actually make that quick trade-off in their mind and participate quickly. Yeah.
Thank you.
We have a question from Lakshmi. Please feel free to ask the panelists.
Maybe Arvind wanted to ask something that, I don't want to hog all the time. If he wants to ask, he'll go ahead and, then I can ask my question.
Arvind just asked, but please go ahead.
Okay. Yeah, so this is a very specific question. I'm digressing a little bit, mainly to Aditya. So in your models that you were showing, did I miss or did you not use any, may I say, classical epidemiology models?
Yeah, yeah. Thanks, Lakshmi. I think, yes, in our current models, they are really trying to give a AI perspective. So we didn't use any mechanistic or traditional models, but that's something which we are trying now, where we are trying to move beyond prediction. And as I said, I think that's also connected to handling some of the data issues, where I think some causality is important. And that's why we were trying to move beyond just predicting the next 4 weeks to, I think, maybe also to more of these what if questions, bridging them with mechanistic models. So we just have a paper out recently. I didn't really talk about it, where we introduce a new class of neural networks which can bridge to these kinds of ODE style models. So we were also working on something bridging them with agent-based models. But yeah, I mean, the results I showed there were purely statistical and AI-based.
Yeah, yeah, thanks for the clarification. I think it's also an important point because sometimes these models, the classical epidemiology models, are used even for prediction. And you were able to show that using totally AI and, you know, kind of learning methods, you're probably doing as well or maybe better than these methods, right? So my point is that I think AI in some sense is showing its power in terms of where it can do. It is doing as well as maybe classical methods. For example, if we didn't have AI methods, we would do similar predictions with the epidemiology models, right? And your point, maybe, I don't know if you made it that way or not, the way I see it is that if you have enough data, you are able to replace some classical approaches by getting equally good results. In a limited sense, in a prediction, of course, counterfactuals and what if cases scenarios would be difficult if you don't take mechanistic ones into account. But even then, I think it is an important point coming from the methodology or from the AI perspective.
Sure. I think I would also maybe frame it as it enables new kinds of problems, right? Like, let's say, revision dynamics itself, right? I think that's really a problem which would be very probably non-trivial for a mechanistic model to handle from first principles. So I would say it's not just saying that I think it enables usage of data in more open and creative ways, probably because I think the technology allows you to compose and many modules right on top of each other. So yeah, that's how I would also frame it. Like, it opens up new ways of doing some of these things.
Yep. Thank you.
I think we're coming close to our scheduled time, and this is turning out to be a really interesting discussion. And I'm sure the audience here are so passionate about data consideration that we can go on and on and on and have really interesting, insightful discussions. I wanted to close, and before closing, ask our panelists to share a thought on one question that is, we're thinking about data considerations within the HPC and constraints or HPC environments. If there was one thing that you wish you could have, or one constraint you could loosen, or one kind of service that you would need on these kinds of environments to get either new science done or facilitate the work that you're doing or have better facilities, what might that one thing be? I'll start with Kirk and then Phil and then Aditya.
Yeah, so I think, the biggest inhibitor between the HPC community and the people that use this is that, it's sort of, you start out with the people that are the users on sort of small, systems, but easy to use, okay? And then they see how hard HPC is, and so it's that they kind of push back on that. And what needs to happen is get the two communities together and go, how can we address these questions? And let's remove the data differences.
Okay.
That's what I think would really help a lot.
Wonderful. Thanks, Kirk. Phil?
So that was a really good question, Venkat. And I think I need more than a minute to think about it. Maybe I should have been thinking about it, more. So I think, I guess maybe riffing off of Kirk's response in terms of, the constraints, and maybe what, a little bit about what Madhav said. If there was a way, to serve all the users equally on these systems while eliminating the constraints of the resources. I mean, so this is pie in the sky, maybe kind of a thing, but I guess it goes towards part of my answer to Madhav about, we have access to some sort of unlimited resources in the cloud effectively. We have, fixed resources that we have on the supercomputing sites, and is there a way to organize things so that we can effectively release those constraints for the people that really need that to facilitate their work? And and if I had a second one, it would be to be able to do that in a way that didn't require any expertise to specifically to use and run those systems. So those are very high level wishes there. But clearly the friction that we run up against is constantly the limitation of the resources and the expertise needed to use them effectively. And so if we can find ways to release some of those constraints, as I said to Madhav, I think we're that's a long-term kind of a thing, but moving towards that I think is a valuable thing to consider. What are the steps how do we get there?
Fantastic. Thanks, Phil. Aditya?
Yeah, sure. I mean, I think briefly, I would agree with Kirk and Phil, and I think of it like bringing the data producers and the consumers closer to each other, right? And in this space, and I tend to look at the other success stories from an AI perspective. If you look at vision and NLP, where I think what has enabled a huge exponential rise in both usability and adoption, and also methodological advances, has been the availability of cheap computing resources, and as well as these data sets. For an average researcher, or maybe your high school student these days, I guess, to just download and participate in a competition, right? So I think there's a lot of, time. I mean, enabling that in a public health perspective would be really, really cool. And I think that will really enable your average AI person to just dive into and contribute new ideas to enable faster, I think, progress on some of these models.
Fantastic. Yeah, thanks for these thoughts, and thanks to the entire panel for sharing all your valuable insights that you've gained over the years and sharing with this, with us and everyone who watched these live YouTube sessions. This has been very insightful. I've found this very, very valuable. So thanks again for joining us. If you have colleagues who miss this talk, they can find them. You can find this on the YouTube channel through the website prepare-vo.org. And we'll see you back again at the same Zoom link at 2 p.m. Eastern today, where we'll have a final session on emerging architectures, which will, in my opinion, will again be another fascinating set of panelists. And I'm looking forward to it. So I'm hopeful that you can also join us and this panel. And again, thank you all for your time and for attending this.
Thank you for putting it together.